Okay, Unit 2, Lesson 5. We're going to start by reviewing average atomic mass. That's where we left off on the last lesson, but it's going to be a couple days with the long weekend that I'll have seen you, so I do want to review that so it stays fresh in our minds. And then we're just going to start talking about electron configurations, and we'll pick up with them in more detail in Lesson 6. So let's get started here. They gave us 3 isotopes of hydrogen, one at 99%, one at 0.6%, and one at 0.4% abundance. They are allowing us to use the mass that's given here. Remember, the upper number is our mass. And one thing that I want to point out to you, when you look at the percent abundances of the isotopes that you're given, see which one has the highest abundance. So for example, protium has an abundance of 99%. When we're done with our average atomic mass should then be closer to number 1. If deuterium were 99% and these numbers were reversed, then we calculated the average mass, then our answer would be closer to 2. So I'm going to do this by just leaving that in percent formation. So it's going to be 99 times a mass of 1 plus 0.6 times a mass of 2 plus 0.4 times a mass of 3. And then I'm going to add all those up, and then I'm going to divide by 100. And what I get over here is 101.4 divided by 100 equals 1.014. So notice how my answer, the 1, is closest to 1, which makes sense because that was the 99% abundance. All right, let's move on to electron configurations. Electrons configurations are a dashed chain of numbers found in the lower left corner of the element box. So we're talking about these numbers right here. It tells us the number of energy levels as well as the number of electrons in each level. So what this tells us is that in energy level 1, there's 2 electrons, and in energy level 2, there are 4 electrons. Now, if you notice, when we talk about the periodic table, periods run from left to right, and groups run from top to bottom. So carbon is in period 2. So the period number also tells us the number of energy levels. If you look at sodium, Na, it's in period 3, and its electron configuration is 281. So the period number, period 3, 281, tells us 3 energy levels. So in carbon's case, period 2, 2 energy levels, 2 in the first and 4 in the second. All electron configurations on the periodic table are neutral, which means that our protons equal electrons. I've told you this before. So let's look for magnesium. If you look at magnesium on your periodic table, and you should have it out, you'll see that it says 282. Notice that these numbers add up to 12, and magnesium is atomic number 12. Magnesium is also in period 3, which tells us that there are 3 principal energy levels. Now, remember what the +2 meant. The +2 meant that it lost 2 electrons, because when I lose, I become more positive. Think of it as weight. When we talk about these guys right here, this one and this one, they are ions. They are ions, which means that they've either gained or lost electrons. You can always tell when something's lost electrons, because when you lose weight, you get smaller and you become more positive. So when magnesium lost electrons, it got smaller and it became more positive. So if it lost 2, its configuration is 2,8. Bromine is atomic number 17. Its electron configuration is 287. If I add these up, it's 17, which is its atomic number. Now, this is a -1, which means it gained 1, because when you gain weight, you get bigger and you become more negative. It's an easy way to remember it. So if it gained an electron, its configuration is 288. Barium is 2, 8, 18, 8. And lead, it says the shortcut allows you to cut out the first 2 orbitals to shorten the address. So you find where lead is on the periodic table and you look at the noble gas before it. You can assume that it has a full electron configuration up to that, so you only have to write what's left, which in this case would be 18, 32, 18, 4. And we will talk about that more. We'll do some examples of these in class. You don't have to worry about these bigger ones on the regents. They'll stay to these smaller ones. Valence electrons are electrons found in the outermost shell or orbital. It is the last number in the electron configuration. So for example, for magnesium, if you look here, this 2 would be the valence electrons, the number in the outermost configuration. And it is the valence electrons that are actually involved in bonding, which we'll talk about in another unit. So in this case, well, all right, I'm going to talk about it for a minute here. When elements combine with other elements to form compounds, there is a sharing or transfer of electrons depending on the elements that are involved. But no matter whether they're sharing or transferring, the bottom line is they all want to be happy, stable, content. And in order to be happy, stable, content, they want 8 in their outermost shell. If you look at all the noble gases in group 18, they all end in 8. That's why noble gases used to be considered inert, and they would never react with anything, because they were already happy, stable, content. They already had 8 in their outermost shell. So everything else on the periodic table wants to either give up or gain electrons or share electrons in order to achieve 8. So magnesium, when it bonds, would technically give up 2 electrons to have 8 in its outermost shell, and then it would be happy, stable, content. And when it gives up those 2 electrons, that's when it forms, like right here, the magnesium plus 2 ion. And I just planted that seed now, but we'll come back to that in the bonding unit. Kernel electrons are the inner electrons. Non-valence electrons. So if we look at sulfur, sulfur has 6 valence electrons and 10 kernel, for a total of 16. So this is its electron configuration, 286. These are the valence electrons, and these are the kernel. Nitrogen has 5 valence and 2 kernel, its electron configuration is 2,5. This is the valence, and then the 2 is the kernel. So principal energy level, or N, electron energy levels that contain a certain number of sublevels. And those sublevels are specific. They are S, P, D, and F. And each sublevel contains a set number of orbitals. That doesn't belong there, that 1. Maximum number of electrons in an energy level is equal to 2n squared, where n is equal to the quantum number or the period number. Remember, the maximum number is 2n squared. 1 squared is 1, so n is 1. 1 squared is 1, and 1 times 2 is 2. 2 squared is 4, and 4 times 2 is 8. 3 squared is 9, times 2 is 18, and 4 squared is 16, times 2 is 32. Sample question, what's the maximum number of electrons that can occupy the third principal energy level? So you've got 2 times 3 squared. So of course that's going to be 18. 3 squared is 9, times 2 is 18. Okay. One method for expressing electron location in an atom or ion is called the Bohr diagram. This is also referred to as the Bohr ring. So all electrons must be drawn. Okay, so first we look up the electron configuration of the element at hand on the periodic table. And if you're working with an ion, you have to add or subtract the proper number of electrons from the outer shells. So carbon is atomic number 6. When we look up the electron configuration, it says 2, 4. So first thing we do is draw the nucleus with a circle and notate the correct number of protons and neutrons inside. So let's do that. So carbon has 6 protons. Its mass number is 12, and 12 minus 6 is 6, so that's 6 neutrons. And then we're going to use the rings or shells, these are your orbitals, and place the number of electrons in their appropriate orbital. So remember that we said it was 2, 4. Carbon is 2, 4. So we've got 6, I'm going to do this up here. 6 protons, 6 neutrons. It's got 2 shells, so I'm going to draw 2 rings. And then we have to add the electrons. So sometimes this is done like this. So there's 2 electrons, and then we have 4 in our outer one. Another way it can be done is sometimes I just like to put the E. So sometimes I'll do this. It's up to you. Really getting messy here. Okay, and that's it for this lesson. Don't forget about your density lab.